Welcome back to this channel for practice problems for actuarial exams. My name is Krzysztof Ostaszewski. You can find information about me at smarturl.it/Jedi. My advice on how to pass actuarial exams is at smarturl.it/pass. This video channel is at smarturl.it/pass actuarial exams. Here you have information about online seminars and study manuals for exams PFM, IFM, and LTAM that I offer. I direct the actuarial program at Illinois State University. You can find information about it at smarturl.it/actuary. If you would like to offer a tax-deductible donation to support our students, please go to smarturl.it/help-ISU-actuary. Here's problem number 1 from the last spring 2019 exam LTAM, the written answer section. ABC Insurance Company issues a fully discrete whole life insurance of $100,000 on a 50-year-old. You are given that the commission is 50% of the first premium and 10% of each subsequent premium. Mortality follows the standard ultimate life table, which of course you can find at smarturl.it/SULT. Interest rate is 5%, which is the interest rate in the standard ultimate life table, and you should always check that. Part A. 1. Write down an expression for L0G, the loss at issue random variable for a single policy, in terms of K60, the gross premium G, and interest rate functions. Part 2. Show that the gross premium calculated using the equivalence principle is 1,270 to the nearest 10. You should calculate the gross premium to the nearest 1. For the later part, we now have the situation that the insurance company realizes that using the equivalence principle premium would create unacceptably high probability of losing money. It decides to set the premium G star using the portfolio percentile premium principle and a normal approximation, such that the probability of a loss greater than 0 on a portfolio of 100 identical policies issued to independent lives age 50 is 5%. Part B. 1. Write an expression for the variance of the loss at issue loss calculated using the premium accounting for benefits and expenses, including benefits and expenses as the payouts, as a function of G star. You should simplify your expression as far as possible using standard actuarial functions. Part 2, show that G star is 1,440 to the nearest 10. You should calculate G star to the nearest 1. And Part C of the question says, without further calculation, state whether the probability of loss greater than 0 on the portfolio would increase, decrease, or stay the same if the insurer sells 1,000 policies instead of 100, each with a premium of G star. Justify your answer. And here's the solution. For Part A, Part 1, L0G, the loss at issue random variable for a single policy, can be expressed in terms of K50, the gross premium G, and interest rate functions as follows. L0G is the present value of the death benefit, 100,000 times 1.05 to the minus K50 plus 1, plus 4G, that's a percentage of premium expense other than the one that is the same every year. So it's 10% every year, but additional 40% the first year. And then 90% of the premium is available to pay for everything, so minus 0.9 G A double dot K50 plus 1 in an angle, so angle K50 plus 1. For Part A, Part 2, using the equivalence principle, we have the expected value of what we just wrote should be 0, and therefore we would have G equal to 100,000 times A50, capital A50, divided by 0.9 A double dot 50 minus 0.4, and we just look up those values A50 and A double dot 50 in standard ultimate life table, plug them in, do the calculation, and we get 1,268.6595, and this is 1,270 to the nearest 10. For Part B, part 1, we note that the discount rate corresponding to 5% is D equal to 0.05 over 1.05, or approximately 4.7619%. And we have L0G equal to 100,000 times 1.05 to the minus K50 plus 1 plus 0.4 G star minus 0.9 G star times A double dot angle K50 plus 1. But that's the same as 100,000 times 1.05 to the minus K50 plus 1 plus 0.4 G minus 0.9 G star times 1 minus 1.05 to the power minus K50 plus 1 over the discount rate, which is 0.047619. And then when we calculate all this, multiply it what we can, we would get 100,000 times 1.05 to the minus K50 plus 1 plus 0.4 G star minus 18.9 G star. That's 0.9 divided by that discount rate, plus, because of minus making it a plus, 18.9 G star times 1.05 to the minus K50 plus 1. So this becomes 100,000 plus 18.9 G star times 1.05 to the minus K50 plus 1 minus 18.5 G star. Therefore, the variance as a function of G star is the variance of what we just calculated. Well, the constant term doesn't produce any variance, so we only look at the random part, which is the part that involves K50. And that becomes a variance of 100,000 plus 18.9 G star times 1.05 to the minus K50 plus 1. And that's 100,000 plus 18.9 G star squared times the variance of 1.05 to the minus K50 plus 1, which is the variance of life insurance issued at age 50. So it's 2A50 minus A50 squared, and of course the constant term is squared in front. For part B2, we have the expected value of that L0G equal to 100,000 A50 plus 0.4 G star minus 0.9 G star A double dot 50, and from SULT we find that to be 100,000 times 0.18931 plus 0.4 G star minus 0.9 G star times 17.0245, and that ends up being 18.931 minus 14.92205 G star. And the variance, well, we just figured out what it would be, but we can find the values of 2A50 and A50 from the table, so we plug them in, and we calculate this to be 0.0152417 times 100,000 plus 18.9 G star, and the whole expression squared. And the standard deviation of L0G is the square root of that, so that's 12.345.738 plus 2.333444 G star, approximately, after we do all the calculations. And let L be the aggregate loss at issue for a portfolio of 100 identical policies issued to independent lives age 50. Then the expected value of L is, well, approximately, because the previous calculation was approximate, so I had to correct this. E of L is not 1,000 times E of L0G, but 100 times E of L0G. So I just replaced that typo, remove the 0, which was a typo, times 100, so it's 100 times 18.931 minus 14.92205 G star, and that's 1,893,100 minus 1,492.205 G star, and the standard deviation is the square root of 100 times the standard deviation that we calculated before. So that ends up being 123,457.38 plus 23.333444 G star. Now we want to find G star such that the probability at L is less than or equal to 0 is 0.95. Note that we assume that since the individual lives are independent and identically distributed in terms of the probability distribution of future random lifetime, the distribution of the aggregate loss at issue can be approximated by a normal distribution with the same mean and standard deviation as L. This is based, of course, on the central limit theorem. Therefore, using the common notation of z for standard normal random variable and phi for the cumulative distribution function of a standard normal random variable, we have 0.95 is equal to probability that L is less than or equal to 0, and that's what we want, and that's probability that L minus its mean divided by its standard deviation is less than or equal to 0 minus that mean over that standard deviation. And of course now the left-hand side is L, which is approximately normal, but it's standardized, so it's approximately standard normal. So it's a probability that z is less than or equal to 0 minus the mean over the standard deviation. And of course that's going to be equal to the function, the cumulative distribution function of the standard normal random variable applied to that number. So it's minus the mean over the standard deviation. But we know from the table that is given on the test, the SULT table, that the 95th percentile of the standard normal distribution is 1.645. Therefore, that expression, which is minus the mean over standard deviation, is 1.645, from which we solve for G star, and G star is equal to 1.645 times 123, 1,457.38 plus 1,893,100 divided by 1,492.205 minus 1.645 times 23.333444. That is approximately 1,441.8465, and that's 1,440 to the nearest 10. Part C, Part 1. Let L stand as before for the aggregate prospective loss, for this time for n policies. We have the expected value of individual prospective loss as before in the standard deviation. Let's just write mu for the first and sigma for the second. E of L for the aggregate loss is n mu, and sigma L is the square root of n times sigma. So 0.95 is equal to probability that L is less than or equal to 0, which is equal to the probability that L minus n mu over sigma square roots of n is less than or equal to minus n mu over sigma square roots of n. That's the probability that z is less than or equal to a minus mu over sigma square root of n, and that's equal to phi of minus mu over sigma divided by square root of n. And this expression, minus mu over sigma divided by square root of n is equal to minus mu over sigma times square root of n, decreases eventually to minus infinity as n increases, because the cumulative distribution function of the standard normal distribution is a strictly increasing function. Smaller values of its argument mean smaller probabilities. Thus, if a company sells more policies, each with the given premium G star, probability of a positive loss decreases. Note that the question as stated does not say that the premium G star would be modified, and it was derived as a percentile premium, so if it's recalculated for a new number of policies, it will change. As the size of a portfolio increases, the percentile premium decreases for a given probability of a loss, and as the size of the portfolio tends to infinity, the percentile premium converges to the equivalence principal premium, which in this case equals approximately 1,268.66. Please remember, this is copyrighted material. The problem itself belongs to the Society of Actuaries. The solution is mine. Good luck in your studies and good luck on the test.